Hi, this is David from Chunke Water Treatment. Welcome to our YouTube channel. Today I will explain to you 10 steps of designing reverse osmosis system. Here we go. First, evaluate feed water source, feed water quality, and treated water quality. As you know that in Earth, only 2% of water is fresh water. All other water, such as underground waters, river water, sea water, ocean water, lake water are not suitable direct to drink or use in your application because these waters has dangerous inorganic and organic compounds, bacteria and viruses. So we have to purify these waters. You have water source. First, you must know more about your water. The best way is send one bottle of water to test laboratory in your city. They give you analysis report, something like this. From this report, first check your TDS level. TDS means total dissolved solids. For more details about TDS, I suggest you to watch this video. I put link below in description and here. As regards to your application, which TDS level you want to achieve or treated water, such as if you use treated water for pharmaceutical industry, TDS level must be less than 1 ppm. If it's for irrigation, TDS level must be less than 500 ppm. If it's for drinking, TDS level must be around 100 to 500 ppm. Second, determine the flow type. There are two flow types, plug flow and concentrate recirculation. Normally, all of our systems are continuous plug flow. In plug flow, feed water passes once through the system. Here see your plug flow diagram. Feed water passes membrane elements and you get permeate water and concentrate water. But sometimes, if possible, increase permeate quality and efficiency in all systems, we send back concentrated water to feed water source. This flow type is concentrate recirculation. It is depend on concentrated water TDS level, membrane recovery rate, and membrane type. Here you can see concentrate water recirculation type reverse osmosis systems diagram. Determine the flow types need experience and technical knowledge. Third, select membrane and membrane type. Elements are selected according to the feed water salinity, feed water falling tendency, required rejection, and energy requirements. The first factor that has to be considered is the feed source. If the feed is brackish water, BW types RO membrane must be selected. If the feed is seawater, CW types RO membrane must be considered. TDS for brackish water is between 1000 to 15,000 milligram over liter, and in seawater is more than 15,000 milligram over liter. Meanwhile, milligram liter and ppm is same unit. 4. Selection of design flux. Reverse osmosis systems are designed as regards to specific permeate flow rate and recovery rate. Recovery rate means how many percent of feed water becomes permeate treated water. The factor which has the greatest influence on the membrane system design is the falling and scaling tendency of the feed water. To learn more about falling and scaling, I suggest you to watch our video in explanation section, and here I share the link with you. A membrane system should be designed such that each element of system operates with a range of recommended operating conditions to minimize the falling rate and to help avoid mechanical damage. These element operating conditions are limited by the maximum recovery, maximum permeate flow rate, minimum concentrate flow rate, maximum feed flow rate. Here there is a table for flux rate. As regards to SDI, silt density index, some RO membrane manufacturers suggested flux rate. Now we see how to use it, such as you have well water. Your SDI index is less than 3. Your system average flux as liter over square meter hour is 27 to 34. 27 is minimum flux rate and 34 is maximum flux rate. And maximum element recovery rate is 19%. 5. Calculation of module number. To calculate module number, we have to know permeate flow as cubic meter per day, membrane active area as square meter, design flux as liter over square meter hour. Permeate flow is your machine capacity. How many water do you need per day? Membrane active area, you can get it from membrane supplier, RO membrane specification, and design flux liter over square meter hour. I already give to you in table. After determination of the module type such as CW or BW based on the feed source and TDS, you can select from the catalog. You can get important information in the catalog such as specified performance, general product description, and product use and restriction. Such as we use DuPont FilmTech BW30400 element specification. I leave a link also you can download from their official webpage. Here we see active area is 37 square meter. Permeate flow rate is 40 cubic meter per day. Salt rejection is 99%. Also here membrane size, you can see it. Diameter C is 7.9 inch. It is nearly 8 and length A is 40 inch. So it is called in market as 8040 membrane. Now we make one example. Don't forget, if you design a reverse osmosis system 250 to 2000 liter per hour, you should use 4040 size element. 3000 liter per hour and more, you should use 8040 size element. To calculate element number, it means reverse osmosis membrane number, we use this equation. Ne equal Qp over F times Ae. Such as we have surface water, SDI index is less than 3, we check our table. Flux rate is 20 to 29. If you want to calculate maximum number of elements, you should use 22. For minimum number of elements, you should use 29. Such as we need water 6000 liter per hour. This is our permeate flow rate, Qp. Our well water TDS is higher than 10,000 ppm. It is brackish water. We choose BW type membrane. This is DuPont FilmTech B30400 element specification. Active area of element is 37 square meter. Now we use equation and put the number in equation. After we put the numbers, we calculate minimum number of element 6, maximum number of element 7. As you see, for 6000 liter per hour system, you can use 6 pieces reverse osmosis membrane. Step 6. Calculation of pressure vessel number and need. Total number of pressure vessels needed equal to total number of modules over number of modules in a pressure vessel. The calculated number should be rounded up to the nearest integer, such as you find number 5.89, so you can use 6 vessels. For large systems, 6 element vessels are standard, but vessels with up to 8 elements are available. For smaller and or compact systems, shorter vessels may be selected. Small system like 250, 500 liter per hour, just one 40-40 or 2 pieces 40-40 elements can be enough. Such as if we go our 6000 liter per hour reverse osmosis system example, we found that we need 6 RO membranes. If we choose 2 elements membranes housing, we need 3 membrane housings. Meanwhile, membrane housing and element vessel are same thing, every country using different term for it. 7. Calculation of recovery, S. Recovery is the ratio of permeate flow to feed water flow, is calculated as this equation. With increased recovery, the pressure may increase somewhat, but the brine will be more concentrated, which can make disposal more difficult. Now it becomes more technical part, maybe get 1 cup of coffee and focus on details more, because it is very important part. As Chunke, we design system to get best recovery rate with lower energy consumption and longer membrane life. It makes us different than other water treatment companies. Sometimes customer told us they got cheaper price other supplier for same capacity, but when we check it, the design is completely wrong. As a result, high energy consumption, low membrane life, unstable permeate flow rate and quality. Okay, now we return to recovery rate. In RO system, Recovery is a function of salt rejection. The rejection capabilities of RO membrane are specified with either a percent salt rejection or a molecular weight cutoff value. Salt rejection is typically used for RO membrane as this equation. Rejection is dimensionless and expressed as a fraction. Cp equal to concentration in permeate. Cf concentration in feed water. Rejection can be calculated for bulk parameters such as TDS or conductivity. Maybe it is better to explain with an example, such as we have brackish water. Its TDS is 12,000 ppm and we want to get permeate water for irrigation as 520 ppm. We use BW membrane and its salt rejection is 97%. We have equation. If you don't know how to use logarithmic and exponential number calculation, you can easily do with trial and error method. In this method, you give value to S. For brackish water system, recovery rate between 0.40 to 0.70. So we start with 0.45, 0.50, 0.55 and then we reach to 0.56. It means 56% recovery rate. If you want to understand how to solve it, you have to study a little bit mathematics. Don't afraid, it is not difficult. 8. Calculation of states. The number of states define how many pressure vessels in series the feed will pass through until it exits the system and is discharged as a concentrate. Every stage consists of a certain number of pressure vessels in parallel. Here, there is a stage table. Here I will give you two tables for brackish water and seawater. You can use these tables to choose right stage number and recovery rate. But normally we are using ROSA or Wave software to be sure stage number. 9. Determine the ratio between states R. The relation of number of pressure vessels in subsequent stage is called the staging ratio. We show it with R. For a system with 4 vessels in the first and the 2 vessels in the second stage, the staging ratio is 2:1. A 3-stage system with 4, 3 and 2 vessels in the first, second and third stage respectively has a staging ratio of 4:3:2. In brackish water systems, staging ratios between 2 subsequent stages are usually close to 2:1 for 6 elements vessels and less than that for shorter vessels. In 2-stage seawater system with 6 element vessels, the typical staging ratio is 3:2. The ideal staging of a system is such that each stage operates at the same fraction of the system recovery, provided that all pressure vessels contain the same number of elements. The staging ratio R of a system with n stages and a system recovery S as fraction can then be calculated with this equation. The number of pressure vessels in the first stage can be calculated with the staging ratio R from the total number of vessels. 10. Balance the permeate flow rate. The permeate flow rate of the last module of a system is normally lower than the flow rate of the first element. This is a result of the pressure drop in the feed channel and the increase of the osmotic pressure from the feed to the concentrate. Under certain conditions, the ratio of the permeate flow rate of the first element and the last element can become very high. These conditions such as high system recovery, high feed salinity, low pressure membranes, high water temperature, new membranes. The goal of a good design is to balance the flow rate of the elements in different positions. This can be achieved by the following means: boosting the feed pressure between stages. Apply a permeate back pressure only to the first stage of a 2-stage system. Hybrid system. Use membrane with lower water permeability in the first position and membrane with the higher water permeabilities in the last position. Example, high rejection seawater membranes in the first and high productivity seawater membranes in the second stage of a seawater reverse osmosis system. I want to tell you again, if you design the system according to these steps, there is a probability that the design system has some problems. So it is necessary to analyze the system using some software such as ROSA or WAVE to fix the errors. Because as water treatment manufacturer, all systems, first we check with software to see is there any design problem. It is very important. If you want to learn how to use these softwares, please write in comment. Now our video is finished. Hope you like it and useful for you. As you see, we are giving high effort to make this kind of video. To make us happy, please hit the like icon and don't forget to subscribe our channel. Thanks. See you next video. Bye.